We are familiar with the concept of field and its connection to charge distribution. Field is considered as an intermediary to calculating the force on a test charge. So if I know the the effect due to all of the charges at any point, if I place it test charge, then I can calculate the force. And hence, it is the effect of a charge distribution considered as a source of the field on any point in space is what constitutes field. One can ask the question, how real is field? Force is real, but how real is field? Or is it just a mathematical or conceptual apparatus? Well, in this course, we'll give it a reality and avoid the question of what is real, because then we'll have to discuss what reality means. So we'll avoid that philosophical question, but it's an important question. So let's get to see if I want to do all of the charges, and these charges to start with, let's say they are discrete. Okay. For example, let's say I have this is my origin, and there are a bunch of charges. They are point charges, and I want the field to be calculated at a certain point. Okay, let's say P. Then let's define our variables from the origin to the point P. From the origin to the point P, this is the vector R. Mark the symbols, all right? And let's say this is my Qi, the charge Qi. Let me not write it there. Okay, so this is, let's say, Qith charge. And then this vector is Ri prime. Okay, and so this is my source charge, and this is the R, the curly R, the R that Griffiths uses is Ri. Okay, so remember, this is so prime, we use the prime coordinate, okay, for the sources from the origin. If this is the origin, then the prime coordinates is the source, this is the source, and this is the field point. In fact, it is so important that let me even write it down. Okay, so this is the source point, and this is the field point. Especially note the symbol that I comply with Griffith, that the source to field vector is of this kind. Okay, this helps in writing it, because you always don't have to write Ri minus R as the vector. Okay, instead you just represent that, meaning what is really the Ri in this. So Ri or R is okay. So this is the R vector for the field point minus Ri, the source point at the prime. So the primed coordinates we call as the source points. Okay, so this is a symbol, and we'll follow this as much as possible where there is possibility of confusion. In that case, okay, how do I write down my E of R? The field as a, so this is R, that's the point P, okay, and of course I avoid writing this constant K1 and K2 and all K, so we write 1 by 4 pi epsilon naught whenever throughout, all right, because this helps me also cancelling factors and is important. So this is just, the source of all of the charges. So I'll sum of each. So this is Qi by R. I'm not writing it properly. Okay, Ri square, Ri vector, and I can be in discrete charges. So it could be 1, 2, let's say n. All right. So that's, and the Q is the test charge. But if it is a continuous charge distribution, okay, then these Qi's should be, and the summation should become an integral, and the continuous charge distribution we can consider as E, okay, 1 by 4 pi epsilon naught. This will become an integral. So this is dq, the source, and this is r square r hat. This is just writing in continuous distribution. And so this actually leads to our, and what is dq? dq would be lambda dl prime for line charge, and dq would be sigma dA prime for surface charge, and dq would be rho d tau prime for volume charge. So this is let's say line charge. This is surface charge, and this is volume charge. So that's just a simple extension. In that case, okay, I can now write down the full for each of them, the E. Okay. I repeated this, but this is, so the first part would be just. Okay, so it's worth pointing out again that, remember, this is source coordinate, and hence lambda is a function of the source coordinates. This is the distance from the source to the field, and this is the vector, unit vector from the source to the field, and the integration is over the sources, because all charges which produce the field. So this is prime, okay, prime. All right. So now, so this statement itself is equivalent to Coulomb's law. This is an integral form of Coulomb's law of a distribution. The distribution could be discrete, or it could be continuous. Now, at this stage, let me point out, when I say a line charge, which means it's a sort of only one dimension line charge, the other two dimensions are not there. Normally we have a 3D space. Now, when do I consider line charge? If the dia, okay, is small as compared to the analysis distance, okay, is small as compared to the distance you are interested in. Okay, for example, at sometimes, when do you consider something a wear, and when do you consider the same wear to be a, let's say, cylinder? This wear is some dia. So depends on the relative distance For example, if I have a point, okay, which is very close to the wire, it's possible that I should treat it as a cylinder. But if the distance is far, then it might look like that wire would do. So that depends on the distances that we are interested in. Similarly, for the surface charge, okay, for the surface charge, so when it's how thin should be surface? How thin? Well, thin enough for the analysis. For example, we could have line charges can be as thin as a carbon nanotube. So a carbon nanotube, or what is its dia? Carbon nanotube dia is about let's say 4 nanometer dia, or 0.335 nanometer. Or it could be a strand of hair. But the same strand of hair can be considered as a cylinder, and so this is typically 1 micron. All right. So it depends on the compared to the distance that of analysis. Okay. Distance. Okay. Now, how thin is surface charge? When we consider that, for example, okay, let's say, what are the examples of a surface charge? For example, a piece of paper in photocopier, paper is charged with a corona discharge. Now, paper for our analysis in a photocopier can be considered a surface charge. But graphene, single layer of graphite that we can extract, it's called graphene. Single layer of carbon extracted from graphite, which is layered. So one layer of extracted from graphene, the graphite is called graphene, and what is its thickness? Is about 0.335 nanometer. And what is the separation between consecutive layers in graphite? Is about 0.14 nanometer. Okay. The surface of a metal, we will see later that charges accumulate on the surface of a conductor. Okay, and that's a surface charge. And typically it might even be thick of few atomic layers. Okay, so it could be as thick as paper, or it could be few atomic layers. Okay, so and the volume charge, of course, it could be a metal ball, or it could be even a 0.33 nanometers of let's say fullerene. All right. Now the next question is, so I'm just trying to once for all bring this out. What is infinity? Infinite charge distribution. Sometimes for convenience, okay, this is a relative distance between the field and the source point. For example, it could be just a 1 centimeter line of charge, let's say lambda, but if the field point is let's say this distance, if this d is much less than the length of the filament, then we can consider it to be infinity. Okay, so it is this d between the field and the, okay, so L need not be infinity, it is just the ratio, okay, between L by D. If L by D is very large, then we can consider it to be infinity. Similarly, for a surface charge, if there is a surface and you are very close to, it need not be flat, okay, and it need not be infinite, Okay, sense of infinity comes from the distance between the field point, and if you are very close, you are in microns, and this is in centimeter by centimeter or millimeter by millimeter, to a distance of 1 micron for the field point. Okay, centimeter or millimeters is infinite for most analysis. So when we say a large plane or a long charge, which means it has to be considered as infinite. It doesn't mean that the charge actually goes into infinity. Of course, we are aware of this, but it's best to explain, and I will point out phenomena as we go along. So they are extremely useful. They are not merely idealizations. In practice, it is extremely useful when we say a line is to be considered as infinity or a plane is to be considered as infinity. That's what I wanted to point out. Let's take one example of the equations that we have just write down. I'll probably take one example each, but let me first take one example, and let that example be a lambda ring with charge density, okay, which is a linear charge density of lambda is equal to cos phi. And what do we have to find out? Find the electric field on the axis. This probably you have done earlier, but I want to illustrate the way I want my answers, the way the systematics and the symbols of how to write an answer also would be clear. I would like to make it clear. So let us first, of course, there is always a diagram. Okay, a neat diagram with a solution goes a long way in. Okay, and then there is from the center on the axis. I want. Okay, so let me. That would be a better if I can do. All right, and this let this be the source dl. So so I'll write down here, this is, let's say, dl prime. Okay, so charge is lambda dl prime. Okay, and where I want the field point is, let's say, here. Okay, so I draw the vector. This is my, what vector is this? This is my r source. This is my field. This is my field point, and this is my source. This is the point P, let's say, where I want the field to be calculated on the axis. This is at a height z, and this is, and what is the length of lambda dl? So lambda dl prime is, this is r, so this is lambda r d phi. All right, so if I consider this to be, I put an axis x, y, and z. Okay, now, so what is r then? R is, of course, root over z square plus r square, and I can clearly see that there would be an electric field in this direction, and so it will have a component, and so this angle, let it just be called alpha. Okay, so then I can write down even a sine. So all the points that are sine alpha would be z, sorry, sine alpha would be, so we'll have to both cos alpha and sine alpha. So cos alpha would be z by root over z square plus r square, and sine alpha would be r by root over z square plus r square. So all the quantities that I really need from my diagram is right here. Then I will write down my dE. Okay. So let me write it down, my dE. This is only due to the differential element, and hence I can write down this 1 by 4 pi epsilon naught. This will be lambda r and d theta. Okay, r d phi, we are saying r d phi, and I can write down root over. Okay, so let me straight away write down here in terms of z square plus r square, one coming from square coming from the r square, and from cos alpha and sin alpha coming this. So this is 3 by 2. Okay, so and then z k, let's say, and you can resolve it in k and directions. So this will be minus r cos phi I and plus r sin phi j. Now r by this is sin alpha, I have already taken into account. R by this sin alpha, and this is z by this, z square r square is cos alpha. So basically a cylindrical problem. I have now resolved the force. This is the dE, this is dE, okay, in ijk. Okay, now let's so all that we need to do is to integrate. Okay, and the integration is only over d phi. Okay, so that's a simple integral, and let's write down then E. Okay, on the axis, this is E at this point z. Okay, is of course 1 by 4 pi epsilon naught lambda r by z square plus r square 3 by 2, that's common, and integral so let's take out lambda naught. Lambda, now expand lambda is equal to cos phi. So this will become z cos phi, this is k, z cos phi d phi. So I have just expanded lambda to lambda naught. Okay, and then plus the r sin phi. So integral j, I have taken this term, r cos phi sin phi d phi, and minus integral cos square phi d phi. Okay, so this is r cos square phi d phi. So each one of them, of course, is from 0 to 2 pi, from 0 to 2 pi. All right. Now this integral, you can see, it's quite easy to do, because k, okay, this is over integral go to 0. This is again cos phi sin phi, okay, which is cos 2 phi, and so it is a full 0 to 2 pi, so this will also go to 0. And what you are left with, the integral of cos square phi, and that is simply pi, from 0 to 2 pi. Okay, just convert it into cos 2 phi plus 1 by 2 and 0 to 2 pi, and that would give us, so we can straight away write down, this will be clearly I, here is I, so here is minus I 1 by 4 pi epsilon naught lambda naught, there is an r coming out from here, so lambda naught r square, and the integral from 0 to 2 pi is giving pi, and z square plus r square 3 by 2. So what survives after integration is really only the I. This is important, that only the I. Could I have, so that's, which means that this is really pointing in the net is pointing in this direction, minus I direction. Okay, so as far as answer that is concerned, but we need to discuss this answer. Okay, so let me write down this as the answer as Z. So could I have anticipated this answer right from the beginning? Well, this when we say a circle, okay, and lambda is equal to lambda naught cos phi, which means you had a charge distribution which is like at phi is equal to 0, like plus. Okay, so slowly becoming 0 towards phi. Okay, let's say, and minus here, minus. Okay, so you can think of even if we had thought of even at the center, it would have been like a dipole. You can see that, right? One side is plus, one side is minus, so it would be here also, it would be pointing in this direction. So it is not surprising that even here it is pointing in this direction. All right. How about z is equal to even lower? Okay, that also, if z is equal to minus also, this point in this direction. So everywhere on the axis, it is pointing in minus I direction. Okay, and effectively, it's looking like as if it's a dipole. Okay, and in fact, one can write it down for a very long for z in terms of the dipole moment of this charge distribution, but that will be going ahead of my story. Okay, we will relook at it. Now, when I am cancelling out this 0, does it make sense? Of course, the k component will become 0 because of the minus side will pull this in this direction, and that exactly for each dl here, there is another dl in the minus side, exactly similar. So those two components will cancel. All right, and in the j direction, of course, they will cancel because of the symmetry. So there's indeed, or what survives in each case is the cos square phi. So this is a simple example, and what I want to illustrate is that you should have from the symmetry point of view, and as a strategy, early on I decided, because of the component and because of the nature of the distribution, that it is best not to keep the cylindrical symmetry but go over from the cylindrical symmetry to the Cartesian coordinates. Okay, because I could anticipate that most of the contributions is going to cancel out. All right. So in solving problems, okay, let me give a tutorial advice at this stage. Okay, in solving problems, it is important to have the symmetry is the first thing that one looks at. Okay, so because that decides the coordinate system, that decides what the answer would be like, the symmetry. Then the strategy, whether you are going to okay, depending on which principle you to start, and then the symbols. Okay, so the symmetry, strategy, and the symbols. Then after getting the answer, this is before the while formulation, but after getting the answer, the limits and extensions. One should look at the limits and extensions. For example, in this I could actually, if I already done dipole, then I could have find the dipole moment and make sure that it's indeed and this limit of z very far, z is equal to 0, the center of the circle in the same plane, and so on and so forth. And then of course every problem has a moral of the story. Moral of the story or the problem. Okay, because and that is what this problem is not a problem, or example is not an example just to solve and get an answer, but there is a moral to the story, and quite often one can look at assumptions which made this possible. Okay, assumptions implicit in the problem, and because of those, if those assumptions are not there, which are the crucial assumptions? One is to simplify, the other is if not there, the problem could not be solved. So assumptions of traps. Okay, so one has to actually discuss all of these aspects to each of this problem that helps, and then only a small number of problems will help you. I have seen in students this craving for solving hundreds of problems on one concept. Okay, that's not required. If you take a representative number of problems and apply and go and think about it deeply and make mental notes, okay, of some of these aspects. That is, what is the symmetry? What the strategy did I follow? And the symbols that were required. The mathematics, the integral in this course should always be simple enough that you don't have to worry about not getting an answer because not knowing how to integrate or how to differentiate and so on and so forth. Okay, we want to focus on the physics of it. So I would like you to look at, for example, one can ask this question here, okay, whether I had only for the axis, could I use, okay, a point outside the off axis to solve this? It can be solved, but it's incredibly much harder than what we have done. All right. So, of course, it can be always numerically integrated. Quite often, it can be integrated also, but the integrals are not so simple. So, and that's what I meant by assumptions and traps. Okay. Okay. So now let me take up another example. Let's take up another example. Let me call it, this is 2a 2. Okay. This is, let me go to a one which is uniform disk. Okay. So uniformly charged disk is something that we'll encounter again and again in this course. So let's try and solve it by uniformly charged disk. So, and this is about Coulomb's law. You can solve it in many ways, okay, but let's say Coulomb law, and that is answer is, so this is has sigma. So given sigma, that is surface charge density, okay, find E on the axis again. Find E on the axis. Okay, so let's draw and from the center. So this is Z. Okay, so I want my point P here, let's say, and I want the field, and this is, so clearly this has to be integrated by making rings, okay, and this is at any particular r, or you can say r prime, because the source coordinate, okay, and then what is the field due to a ring, due to ring on this point, due to this circle, okay, not nice, the line, okay, so why is it double line, sorry, okay, this is, okay, so this is my, and then this is my r, this is my r vector, okay, and this is the ring, and then I'll integrate over the ring. That's pretty, the strategy is pretty clear, and so this will be, I can consider this now the angle alpha, this will be the angle alpha, and this will be pointing in this direction. So quite clearly we can use, okay, first a ring. If you have not solved the ring, then you should solve for a ring alone, okay, initially. So let's start by saying that my dE due to the ring, okay, is of course k in the direction only due to the ring, because of the symmetry. It will be in 4 is a uniform ring, so 4 pi epsilon naught. What is my charge? This is 2 pi r lambda for a ring, okay, and this will be z square plus r square, and of course the component in the k direction, this is r square plus z square. I did not write 3 by 2 here, so half. Okay, so that's the ring that is important to even work out, okay, if you like, okay. So in some sense, how did I write that down? Or it is one can actually generalize to dq. So dq and by the r square plus z square 3 by 2 and z, okay, in the k direction. So if I know for the ring, so now the only thing that you need to do is my dq has to be replaced by the sigma, okay. The sigma would be 2 pi small r or r prime, this is 2 pi r prime into dr and sigma, okay, and hence I can in this course we should be actually using if we're using the cylindrical coordinates SDS, but let me write down then my full dE, for this will be vector k 1 by 4 pi r prime dr prime sigma by r prime square plus z square 3 by 2 into z. Okay, so E disk, this is disk. So E disk then becomes, we can simplify a lot, and let's say k sigma by 2 epsilon naught. This will be integration over r prime is from 0 to r prime dr prime divided by r prime square plus z square 3 by 2. Okay, so and this can be written down. So integral here is fortunately very simple. We can take xi is equal to r square plus z square, giving rise to d xi is 2 r prime dr prime, and so the integral is really between from z square to r square plus z square. If I convert it, then 1 by xi 3 by 2, this is d xi by 2, and that's a simple integral. Okay, so if I plug that in, then I can see that I'm getting k here sigma by 2 epsilon naught, and z is still there, and 1 by z minus z by root over r square plus z square. Okay, so this is also can be written down a little by z taking in, that is sigma by 2 epsilon naught. I'll take z in, and that becomes 1 minus sorry, this was only 1 here because in the integration. So this becomes now z by root over r square plus z square. All right. So that's actually a very useful. Don't remember, we can always get it because it's so easy. So E disk is indeed a very simple expression, okay, on the z-axis. Let's take understand its limits. Okay, that is, if r tends to infinity. So if r tends to infinity, then E becomes a plane. This is a large plane, infinite plane. Then it's for is equal to sigma by 2 epsilon naught k. So from Coulomb's law also we can obtain this. We can obtain, of course, easily from Gauss's law, as you can see later. The same thing can be said if it is z tends to 0. That is, if the point comes to very close to the plane, that also should give you the same thing, and it does indeed. Okay, so the point that I was making earlier, infinity is a relative term, even so this is also 2 epsilon naught k from above. All right. So this is from Coulomb's law. One can obtain for a small disk and then extend it till infinity by taking limits. One could extend this simply there is another limit that we should be we can look at. Suppose z goes to infinity. Of course, we know what to expect. It should look like a point charge. Okay, and that can easily be done by taking z tends to infinity. Then this quantity 1 minus the bracket quantity under the bracket can be written down as 1 by, I can take z out and cancel it, and that becomes 1 plus z square by r square by z square, right? and when r by z, z is large, so z is small, and hence this can be approximated by an expansion, because this is of course half. All right, so then this itself will give you can be made it to be 1 minus let's say 1 minus half r square z square. Okay, so then this and this cancels this, so this is really half r square and z square, and hence E at very large distance becomes of course k sigma by 2 epsilon naught half r square by z square. All you need to do is to multiply a pi upstairs, so this becomes 4 pi epsilon naught and pi r square by 1 by z square, and this is nothing but the total charge, and hence we recover sigma pi r square is nothing but total charge, okay, for the disk, and hence it is total charge by 4 pi epsilon naught 1 by z square as expected. So all the limits are right, and sometimes we need to look at them. I can now extend this disk result, okay, that we have obtained here, this result here, one can now extend it to, let's say, a cylinder. Okay, suppose now I am asked to do for a cylinder of cylinder of height h, okay, let's say this height is h, and this thing is rho. Okay, so and I want it for the point z here, so obviously I'll take a disk somewhere here, okay, and then use the result from here to here. Okay, so this is R now, and so E cylinder, then so E cylinder can then be written as dE disk, and that would be equal to so I, of course it will still be in the on the axis, so it will be still in k, and the integral is from let's say we'll come back to it, so rho dz is the rho dz prime by 2 epsilon naught, that is sigma, this is the sigma becomes this now. So what I am saying, what is z? Z is this point, and z prime is this point because it is source coordinate, and the height is h. All right. So the z and 1 minus, now it becomes the distance becomes z minus z prime by root over, I'm just applying r square plus z minus z prime square. All right, and this is a simple integral, and I can write down the result directly. This will be now rho 2 epsilon naught, okay, and the first term will give me z, and the next term will give me root over, this is of course 0 to h, all right, so that will be root over r square plus z minus h by square minus root over r square plus z square. All right. So this will be E cylinder. On the axis, of course. Okay, it's E cylinder on the z axis itself. So that is. So what I have shown you is that we started from a ring. From ring formula, we started from actually a ring which you can almost directly write it down. Okay, so our original aim was to. So this is the uniformly charged disk. So we started with a ring, and then we derive it for a disk using the ring formula. Looked at its limits, and then one could then integrate over a height h, okay, to make the cylinder. It is let me again point out that the variable choice is important. Okay, z is the field variable, z prime is the one that varies over the source integration. All right. So in this lecture, what we have seen is that whether it is a source field is a point charges, discrete charges, okay, or it's a line charge, okay, in which we get lambda dl, and the point P one can obtain, okay, or point P, and then one can obtain the solution from limited charge, or it could be a surface charge, okay. So from a surface charge, so this would be sigma dA prime, this is sigma d lambda dl prime, and the point charge P, this is R, okay, or it could be a volume, some arbitrary volume, and one could start with a differential element d tau prime, and obtain by integrating. All right. So discrete charge or continuous charge one could obtain from the same Coulomb's law. But Coulomb's law is the basis, but we will now go over to a more powerful way of doing many symmetric things, and that is the Gauss's law.